So you have to, all of you have to verify that how LXA is less than or equal to LA, how RX is less than or equal to RA, how JXY is less than or equal to JA. So this is an assignment for all of you. When LXA is should be less than or equal to, you have to be able to prove this, and this. That's very easy, single line. Second, that LA less than or equal to LB implies JA less than or equal to JB. And similarly, it's a dual case, that is RA then RB implies JA less than. It's a dual case. So second fact is this, very easy, that if L is less than or equal to LB, then it implies JA less than or equal to JB. How? Prove it. Very easy it is. So there are three assignments. That is, you have to prove that these sets are partial ordered. You have to prove this fact and as well as this fact. Now again we will prove that D and J are equal to each other in a particular case. How? See. Before that, first I would like to tell the definition. So one definition is there. A semigroup S is set to satisfy the condition minimum L satisfies minimum L, minimum R, or minimum J according as the partial ordered set S by L, S by R, or S by J satisfies minimal condition. You can say that satisfy the minimal condition. Minimal condition, that is every non-empty subset of S by L, S by R or S by J contains a minimal element, so where basically every subset of S by L, contains minimal element. For example, if S satisfies condition minimum L, then if you consider then S by L, or you can say that every subset of S by L has minimal element, say LA. Another subset may have LB, so like that. So every subset of non-empty subset of S by L, S by R, S by J contains minimal element, and we know what is minimal element. We have studied in chapter number 1 what is minimal element. So now the proposition 2.15 is basically I write in the beginning. If S is a semigroup satisfying minimum L and minimum R, then D is equal to J. So basically we know that D is contained in J. What we have to prove? We have to prove that J is contained in D. So for this what we do, we take a pair of element in J, A, J, B, and finally we show that A, B goes in D. And for this what we have to find out, in the same way we will do that, we have to find out of C such that A, L, C and C are B. So in this way A comma B will be belongs to L composition R, and L composition R is what? D. And also I like to prove, I want to tell this is very obvious that D is L composition R, and also it is R composition L. So if anybody is proving like this, that A, R, C and C, L, B, then it is again correct, because L composition D is equal to L composition R, and also it is equal to R composition L. So for this, suppose that A comma B belongs to S such that A, J, B, then there exists P, Q, R, S belonging to S1 such that P, A, Q is equal to B and R, B, S is equal to A, like this. Now consider set X is equal to X belonging to X such that there exists Y belonging to S, X A Y is equal to B, like this. So of course then this set will be what? Non-empty. Because we know that PAQ is equal to B, isn't it? So P is a member of X here. So always this set will be non-empty, isn't it? and so if you consider another set, Lx such that X belongs to X. Of course, this is a subset of S by L. So this set is again a non-empty. So this is a subset of S by L, and this set is again non-empty because here X is belonging to S, which is non-empty. So this set will be non-empty. Correct. Now, as we know that S is a semigroup which satisfies minimum L, isn't it? So since S satisfies minimum L, therefore minimum L condition, therefore we can choose minimal element. Therefore we can choose minimal element LU belonging to this. Correct. Therefore, we can choose minimal element LU belonging to this. Correct. So now LU is in U. It means what? It means U is in X, isn't it? So U belongs to X. So there exists U belong to X. So there exists V belonging to S such that UAV is equal to V, isn't it? Because U is in X, so it means there exists some V in S such that UAV should be equal to V. Now U are UAVSV. Now this is what UAV is, what B. So URBSV. Now RBS is what? A. So it is UAV. So it is what? B. So URUAVSV is equal to B. Correct? So and so LURU belongs to this. See, because URU into A into U VSV is equal to B, it means what? URU goes in X and A. Of course, LUR goes in this set. Correct? Now you see, now LURU is of course less than LRU and it is less than LU, correct? By the fact we have seen. So LURU is less than is equal to LU basically, isn't it? You can just write simply, you just write here like LU, no problem. Now since LU is minimal element, therefore LURU is equal to what? LU. This we have. So LU is equal to LURU, it is less than LRU, it is less than LU, correct? So it means that here it is LU, here it is LU. It means what? This and these are equal to each other. It means therefore ULRU. Because LU is equal to LRU, it means U and RU are related to each other. Now L is the right congruence, correct? So what we get? RULU, correct? So RU AV LU AV, as L is right congruence. So L as right congruence, so you can multiply on the right side. So right compatible. So RU AV is equal to LUV. That is. This is what? RBLB. We get this. RBLB we get. Now, using similar argument and condition of minimum R, using similar arguments and minimum R condition, what we get? We get BSRB, correct? So BSRB we will get. Now R is what? Left congruence, so we can multiply by left. Since R is left congruence, just I am writing here. So since R is left congruence, so we will get, therefore RBS is equal to RB. And what is RBS? And that is ARRB. So ARRB and RBLB implies what? AR composition LB, it implies that ADB, and that is required. So hence D is equal to G. So okay, I will prove Green's lemma in the next turn. So we stop here. Thanks.